Section 2.1 is on page 80, talks about the derivative and the slope of a graph. Now, derivative is coming up. We want to start with the slope of a graph, and we want to start with the definition of what a tangent line is. A tangent line is something that we will need to use all throughout this course from now on. Is a line that touches a circle at one point, like that point right there, in which the line, this line, is perpendicular to the radius. And remember, the radius is the line from the center to the circumference. So we need to get a perfect graph, but you want to imagine every time they give you a curve with a point, you want to try to imagine drawing a circle, not a perfect circle, in which the line and the point kind of like are perpendicular to the center. And you could see how good this is and how good this is. I expect you to do something like that, maybe a bit nicer, but I don't expect you to do this for sure. So we're going to start off on page 88. Trace the graph and sketch the tangent lines at point x1, y1, x2, y2. So if I go to x1, y1, if I would imagine kind of like if there is a circle. So I really think of a circle right there, and I'm thinking, how can I make a line tangent to that? Well, it looks really flat. So I want a line that touches that curve at one point in which I'm imagining that it's perpendicular to this radius. And then that's fine. And if I get to this point, the same deal. Now, whether the circle is the inside or the outside, meaning I could have did the circle right there. Normally, we let it embed within the curve because the wider the curve is, the bigger the circle is. But again, this is all estimate. If I want to think of a circle touching at one point, I could think of it as right there. So can you imagine a line touching at one point that touches that circle at one point? It seems something like this. Again, not a perfect, but that's acceptable. So that's pretty much it. How about number 4? Number 4 again. Now, I'm hoping on the long run you're not going to draw the circles anymore. There. And if you draw a line, something like that. And if I do it for x2, y2, imagine the circle in my head. Again, the hope is that eventually you'll be able to kind of sketch a line yourself without using the circle. A bit off, a bit on, that's not a problem. That's good enough, that's sufficient. And if I was looking at this, I would imagine it's almost flat, almost. There. And a line, well, here it's going to be hard to really do. It looks something like this. So if you could imagine the circle running this way, you know, and perpendicular, something like that. Or the other way around, the circle's here, it doesn't matter. Now, let's talk about a slope of a line. We're going to go back to the algebra review that we did. And like I said, we only covered what we need for our business applications. So we did this already. Each of those is considered 1 unit. This is approximately the slope of the graph. Approximate the slope of the graph. So what I need to pick a rise and a run. To do that, I need 2 points. I could approximate if I have no choice, but if I could find exact points, that will be ideal. Well, let's see. I could say that's an exact point, and I could say that's an exact point. Do you see that you rise 1, 2, 3, 4 units up? That's positive 4. And you run to the right 1, 2, 3 units. We say the slope of this line is 4/3. approximate the slope of the length of the graph. Do you notice that this is the slope of a tangent line? Because it touches this curve at one point. Same deal with this. This is the slope of the tangent. And that's something we're going to use all throughout. That's actually called a derivative. So to find the slope of this line, we're going to say it is rise over run. The same deal as what we just did. Can I find two exact points? Well, this is an exact point. I can't find another exact point, right? It seems if I go from this to this point, that seems to benefit me more. And the reason for that, it seems I'm raising up 1 unit and I'm running 1, 2, 3 to the right. Again, any 2 points will do, but you need to approximate. So that's not a big deal. We're not going to disagree on the approximation unless you're way off. How about this line? Do you see that line running straight down? Well, that's a point right there. And there's a point right there. Isn't the slope of this line rise over run? Don't you rise 1, 2, 3 units down and you run 1 to the right? So very important to get. Now we get to the applications. Tangents we're going to do. This is the actual calculus. It says the graph represents the sales in millions. Oh, actually, no need to point that. It's right there. In millions of dollars. For Fossil from 2007 through 2013, where T represents the number of years, T equals 7 correspond to 2007. Okay, that's very good. Estimate and interpret the slope of the graph for the years 2010. Let's use 2010 and see how that works. Where's 2010? It's right there. What do they want? They want the slope. If I draw a tangent at that point, now again, we could disagree. That is, my numbers and your numbers could be slightly different. That's okay. We're approximating anyways. Okay, I'm trying to find a slope for this line. I'll say that's a point. And let me see. Do we see another exact point? I see. Actually, right there. So it seems the slope 2000, not 210, 2010. It seems the slope is rise. Each of those units is 500 over run from 9 to 10, that's 1 year. So I'm going to say approximate. This is how you write approximate. Either you put the squiggly line or you put an equal with a dot on it. And what this means that, actually let me do the other one and then we do the whole thing. And say what those mean, because they mean the same thing. How about the year 2012? If I go to 2012, I'm trying to find imagine a tangent right there. That seems to be like a tangent. I could expand that line. So you get a ruler, probably it would be a good idea. And it looks like there's a point and there's a point. Oh, okay. That wasn't pleasant. I was hoping to get something totally different, but it didn't work out. So the slope is roughly also 500. So what does that mean? The slope is the rate of change in millions of dollars of sale per year. Right? So here in the year 2010, we're saying roughly we were selling $500 million. That's the rate of change roughly per year. If the slope goes up, that means you're selling more. Do you notice that if you go a bit lower, the slope is lower? So the sales are going up. If the curve is growing, then that means the sales are going up. Here's another problem. Now we do have a definition to go by. So we look at a problem and it says find the slope of a graph. It says use the limit definition to find the slope of the graph at the given point. Well, okay, let's ignore that point. Graphing this, sketching a graph and trying to pick that off of the graph is something that we did, but we have a definition. If you want to find the slope of the tangent, this is the slope of the tangent. That is the limit as this delta x approaches 0 of f of x plus delta x minus f of x over delta x, or you might have seen it as the limit as h approaches 0 of f of x plus h minus f of x over h. That's called difference quotient. And in section 1.4 we did this already. You could view it. Let me see, 1.4, if you recall, somewhere here, right there, number 30, 34, right? We did the difference quotient right there and right there. So the work we already did, we're just adding the limit. And how are we going to use the limit? We're going to use a limit with our shortcut. So what do you notice happen if you let delta x equals 0? Wouldn't that be f of x minus f of x over 0? Isn't that 0 over 0? And you're taking the limit. And wasn't the shortcut for a limit, if you get 0 over 0, the rule of thumb, wasn't that you simplify? So guess what? Those are going to come back, and let's do 3 of those, the 3 different types, polynomials. So what am I doing? I'm trying to find the slope of a line. I'm trying to find the limit as delta x approaches 0 of the difference quotient. So just like we did in section 1.4, what is f of x plus delta x? If I figure that out here, I'll figure it here. Whoa. If I figure out f of x plus delta x, that would be 11 minus x plus delta x squared. That is, if you FOIL this, x squared plus twice x times delta x plus delta x squared, and that would be 11 minus x squared minus 2x times delta x plus delta x. Oh, I kept the square, I'm sorry. Here we go. So this component is actually right there. If I fill that up, and keep in mind, if I substitute delta x equals 0, I'll get f of x minus f of x. I'm getting 0 over 0 every time, right? So the simplification is going to be for delta x to clear out. So 11 minus x squared minus 2x times delta x plus delta x minus f of x. F of x is right there, whatever this is. Make sure to use parentheses. All over delta x. So that is the limit as delta x approaches 0. And what that would be, 11 minus x squared minus 2x times delta x plus delta x minus 11 plus x squared if you distribute the negative n. And I notice here that 11 cancels with negative 11, and negative x squared and positive x squared cancel out. Limit as delta x approaches 0, that's negative 2x plus 1 times delta x if I factor delta x out. And do we notice that, oh boy, I love this stuff. There it is. I knew something was off. The square was there. It's just I put it on the wrong spot. It's really this square when you FOIL this, right? So that's squared. I knew something wasn't adding up. So when you factor delta x out of those, and we know this is going to cancel out every time. And once you cancel out, what do? Then you restart the limit, meaning you use direct substitution. Take this and put a 0 in place of it, and what do you get? And you get the slope of the tangent to be represented by negative 2x. Okay, what would that be? Well, here's the point. What does the slope of the tangent equal for, and this is how they write it, 1, x is 3 and y is 2, but there's only x in there, so x equal 3. Put a 3 in there, you get a negative 6. And, of course, we're going to tie this to another definition, and they're going to call this the same exact definition, the derivative of f. The derivative of f at x, or f prime of x. So this has many names. This slope of the tangent has many names. Derivative, rate of change, chemical reaction. It depends on the application. Velocity in physics, right? In chemistry, chemical reaction. In business, we have a lot. It's going to figure out the rate of change of sales, the rate of change of cost, the rate of change of profits. Big deal. Slope of the tangent has tons of applications. Now we're just going to find it. Sometimes they call it derivative, sometimes they call it slope of the tangent. I'm going to show you the definition really quick. And you notice the derivative. So the derivative of f at x, f prime, is the limit as delta x approaches 0, f of x plus delta x minus f of x. And what do you notice? It's identical. It is the slope of the tangent. You're not seeing twice, right? It is deja vu, provided the limit exists. And you notice if you put delta x equals 0 right there and there, you will get 0 over 0. So you need to manipulate the problem, and we have 3 types of problems. Polynomials I just did. Find the derivative. If they give us an x value, we'll plug it in. And here they have a radical and a rational. So those are the 3 types of problems that we come across. And I wanted to tackle all 3. Even though we did those already in section 1.4, it doesn't hurt to do them again. Let's do a radical. So what is f prime of x? It's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That would be the limit as delta x approaches 0. F of x plus delta x is going to be the square root of x plus delta x. Don't forget the plus 2. Minus f of x. F of x is simply what you see over delta x. The goal is to eliminate this delta x from the denominator, but it doesn't cancel out. So what you do, you say, alright, with radicals, there's one way of proceeding. You're going to multiply by the conjugate. What's the conjugate of this? The same exact radical, both of them, except you make sure that the sign between them is opposite. That is, if this is negative, you make that a positive. And that would be the limit as delta x approaches 0. Denominator you just copy. You don't have to multiply. The goal out of this whole mess is for you to clear that delta x. The top, since you're multiplying conjugates, you get the first squared. Well, Square a radical, it cancels out. Make sure to use parentheses. Minus this squared. And we know that from factoring, right? In case you were wondering, we know that from right there. If you multiply conjugates, the same exact things, 1 time minus 1 time plus, you get the first squared minus the second squared. You are welcome to FOIL those if you wish. And I'm going to just simplify again. At every stage of the game, I replace delta x by 0, I'll get 0 over 0. So the top will be x plus delta x plus 2 minus x minus 2 over delta x times this whole mess. Limit as delta x approaches 0, those cancel out and those cancel out. Delta x over delta x multiplied by the square root of x plus delta x plus 2 plus the square root of x plus 2, and those cancel out. And you're left with the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus 2 plus the square root of x plus 2. Now, if you replace delta x by 0, you will get 1 over the square root of x plus 2 plus square root of x plus 2. And if you're adding the same thing, isn't that 1 over twice the square root of x plus 2? So this is called the derivative, or the slope of the tangent at any given point. If you give me an x value, I'll plug it in, and there it is. And I have one more. I want to do the last type, which is a complex fraction. We did that already. So here, for g, if I want to figure out g prime of s, I'll take the limit as delta x approaches 0 of g of x plus delta x minus g of x divided by, oh, it should be s. You know, it doesn't matter. It's okay. We keep it as x. That's not a problem. So we could convert it from x to x. No big deal. So that's going to be the limit as delta x approaches 0. Now, delta x is delta x. G of x is right there. Just copy it down, replace s by x. What is h of x plus delta x? Copy it as you see it. Replace x by x plus delta x and a minus 4. This is a complex fraction. We discussed that last time. This is over 1. If you find the LCD for the top and the bottom combined, in one step you could convert the complex fraction into a single fraction. What's the LCD? It's this times this. And if I make every denominator over that, that is, what's this missing? This is missing an x minus 4, so multiply by x minus 4. This is missing an x plus delta x minus 4. And this is missing an x plus delta x minus 4 times x minus 4. And I never multiply the denominators out. Remember that. That's a waste of time. Why? Because I want this to cancel out. It's right there. Well, this will clear the denominators. And you just read the top. Meaning, you transform the complex fraction into a single fraction. 1 times x minus 4 is x minus 4. Negative 1 multiplied changes all the signs, so you distribute negative x, negative delta x, and a plus 4. And the denominator, I'm going to copy all of that mess. And that's going to equal the limit as delta x approaches 0. Now, the 4's cancel out, and the x's cancel out. I'm left with a negative delta x over delta x into x plus delta x minus 4 into x minus 4. And you notice that those cancel out, and I'm left with the limit as delta x approaches 0 of negative 1 over x plus delta x minus 4. And how do we find limits? We always use direct substitution on all of these functions, rationals, radicals, you know, the usual from section 1.5. If you put a 0 there, isn't that negative 1 over, isn't that x minus 4 times x minus 4? Isn't that negative 1 over x minus 4 squared? And there's my homework. My homework section 2.1, page 88. You're going to run numbers 1 through 13, odd number 21, 35, and